parametric differentiation today, I would like to show you one more example. How do we use the implicit differentiation to get the d2y dx2? All right, let's look at question number 58. All right, so question number 58, if you look at this question, the given equation there, you have a special term in the equation, dy dx cube. Okay, so previously some people asked me, if we have this kind of situation, how are we going to differentiate? So the answer is, you differentiate the dy dx cube as usual using the power rule, and remember to differentiate the term in the bracket. Okay, so let's look at how we do this question. So we first start with the equation. So this is question number 58. Okay, so 58, we have the equation x squared x squared plus y squared plus bracket dy dx in the bracket cube equals to 29. All right, so let's say I call this equation 1, yeah, and we are given the point. This one actually passes through the point 1, -1. All right, so they asked us to find the values of dy dx and d2y dx2. So we can first substitute x equals to 1. So you let x equals to 1, y equals to -1 in equation 1. So therefore, I can find the dy dx value. You put in, you get 1 plus 1 plus dy dx cube, and this is equal to 29, right? So after that, what happened is you get dy dx cube is equal to 29 minus 2. So you have 27. So the value of dy dx is therefore cube root of 27. So the answer is 3. All right. Now the next question is, how do we find the value of d2y dx2 when x is equal to 1? So you need to differentiate equation 1. So d dx equation 1. So what happened? You differentiate the x squared as usual, you get 2x. Differentiating y squared, you use the power rule as usual, 2y, but you have an extra term there, which is dy dx. All right. Now, how do we differentiate dy dx cube? The answer is you use power chain rule. So power chain rule states that you have to move the original power down, then the original power reduces by 1, and you have to differentiate the term in the bracket. So the right hand side, if you differentiate 29, you get 0. Okay, so therefore we have 2x plus 2y dy dx plus 3 times. Now the term in the bracket is dy dx, so you just copy. So dy dx, and this one you mean you have to put in dy dx as well. Now you need to simplify this term here. What is this d dx dy dx? That means the differentiation of dy dx with respect to x. Therefore, what do you get? You will get d2y dx2. This is actually d2y dx2. Hence, we obtain the expression. So the expression is 2x plus 2y, 2x plus 2y dy dx plus 3 times dy dx squared. Then you have the d2y dx2, and this is equal to 0. All right. So now you substitute the value. You sub x equals to 1, y equals to -1, and you sub dy dx equals to 3. So dy dx equals to 3 into equation 2. So let's say now we call this equation 2. Okay, and hence you will get the answer 2 minus 2, and then times dy dx, which is 3, and then plus 3 times dy dx, which is 3 squared d2y dx2 and this is equal to 0. Then you should know how to proceed. Okay. So what happened now is you find d2y dx2, and you can proceed with the answer. All right. Can somebody calculate what is the answer of d2y dx2 in this case?
4/27.
4/27. I think the answer is given at the bottom of the question, right? Can you please check? Is that correct? 4/27, yeah? So that is what is that sound? What is that noise? Somebody sneezes.
Corona.
Yeah, I'm scared, you know. Who's that?
Oh, sorry. Forgot to mute my mic. Sorry.
Forgot to mute your mic?
My mic, yeah, forgot to mute.
No need to mute what? But what did you do? You sneeze, is it?
Sneeze.
Oh, okay. So please go to the hospital and check.
Low.
Right, let's move on, yeah? Now, after this question, now we move on to the parametric differentiation, yeah? P3. We start with P3, right? This is parametric differentiation that we learn in P3. Okay, so today we continue from there, right? Okay, let's revise first what you learned in P3. Okay, in P3, we have the parametric equations in the form. Let's say I call this x equals to a function of t, and then I call the y as another function of t. So we have f of t and g of t respectively. So t is what you call the parameter. So what is a parameter? A parameter is actually a variable connecting x and y together, right? So when you have the parametric equations defined separately for x and y, what happens is you can find the dx dt, which is given by f prime of t. You can also find the dy dt, the expression for dy dt. This is given by g prime of t, right? Now I want to introduce a new notation here. The new notation here is actually the differentiation of x and y with respect to t. There's this notation that you can use here. We call it x. Then you put a dot on top of the x. This one means the differentiation of x with respect to t. Then the other one is dy dt. So dy dt will be denoted by y, then with a small dot on top of it, right? So x dot means differentiation of x with respect to t. Y dot means the differentiation of y with respect to t. Now the notation that we use here is different from y prime. If you remember last time, I also told you y prime is the differentiation of y with respect to x. So please take note, they are different. So that's why if the parameter is t, if the parameter is t, then you can use x dot y dot if you don't want to write dx dt and dy dt. Okay, so now what happened is I want to find dy dx. I want to find dy dx. So I proceed with dy dx by chain rule. You write this as dy dt times dt dx. But I told you in P3, we don't do it this way lah. We straight away put in the quotient form, right? So you have dy dt over dx dt. So this is what you have in P3. So you can also write this one as y dot divided by x dot. Okay. Now you have to take note. When you find the dy dx this way, your expression is actually in terms of t. So this is now an expression in terms of t. Okay, so if I want to find d2y dx2, now d2y dx2 means what? d2y dx2 means the differentiation. So to find second derivative of y. Okay, so that means I have d2y dx2. So just now I told you d2y dx2 basically means the differentiation of dy dx with respect to x. So you take note of the variable here. Now you are differentiating with respect to x. But I told you just now, the dy dx here is actually in terms of t. I told you just now, right? dy dx is in terms of t. Therefore, if you differentiate the dy dx expression, which is in terms of t, with respect to x, you cannot differentiate directly. So what happened now is, I use chain rule again. So in order to differentiate the dy dx, which is in terms of t, you must have dt. So therefore, I introduce the variable dt, dt. This is what happened. So now the d dt dy dx, you can differentiate as usual, all right? And therefore, you obtain the form d dt dy dx divided by dx dt. Okay, so this is how you find the d2y dx2 in further math, right? If you look at the what do we call that? The P3 differentiation, they never ask you to find d2y dx2. So you need to remember. You differentiate the dy dx as usual, but remember to divide by the dx dt. Remember to divide by x dot, because dx dt means x dot, so you have to do this. So basically, this is how we find the d2y dx2 for a parametric equation. Okay, so let's move on. We look at one past year question. So we can look at past year question. Question number 40. Last week, I think I talked about 44, 45, something like that. So today, I think I want to talk about 49. So you look at question 49. Okay, so you look at question 49. You read the question first. Okay, question 49. It is given that x and y are functions of t given there. And then they told you the domain for t. So the domain of the parameter is in between negative pi to pi. So find dy dx in terms of t. So how do you find the dy dx in terms of t in this case? This is actually a P3 question. So you should know how to find dy dx by using chain rule. So basically, you have to find x dot and also y dot. So we look at question 49. So question 49, you have x equals to t plus sine t. You have y equals to t squared plus 2 cos t. Now these are the two equations given, all right? And then you look at the result at the bottom. Now I always encourage you to actually read the entire question before you start planning how your solution looks like. So you read the question, the second part, all right? The second part of the question. Show that d2y dx2 equals to 2t sine t over 1 plus cos t cubed. You look at the trigonometric term there. You have sine t, you have cos t, right? So in this case, it gives us a hint that we do not need any double angle formula or half angle formula. So in this case, it would be very useful if you start defining, you let S denote sine t, and you let C denote cos t. That will make your solution shorter, rather than keeping writing sine t, cos t, sine t, cos t, right? So now we can start with x dot. So the x dot means the dx dt. Differentiating t, you get 1. Differentiating sine, you get cos. So you have x dot equals to 1 plus t. Furthermore, you can proceed with y dot. So y dot is equal to differentiating to t squared, you get 2t. Differentiating to cos t, you get minus 2 sine t. All right. So you can say this is actually 2, and then t minus sine. That's all. T minus sine. Or you cannot cancel anyway. Okay, doesn't matter. So by chain rule, so you can proceed with the chain rule. So you have dy dx is actually given by y dot divided by x dot. So y dot divided by x dot means you have 2 t minus s over 1 plus c. So the dy dx is found. Done. That is the first part. Now the second part is d2y dx2. So d2y dx2 is equal to 2t sine t over 1 plus cos t cubed. Now the expression is given. So they expect you to do to give all steps. They expect you to write down all the steps. All right. So try not to skip any step. So we start now. Now, like what I told you just now, to find the d2y dx2, to find d2y dx2, this is equivalent to, you have to differentiate our dy dx, which is in terms of t, with respect to t, and remember to divide by the x dot, the dx dt, right? This is the chain rule. So we have 2 steps here. Step number 1 is to find this one. The d dt dy dx must be found first. So this one is step number 1. Step number 2 is the entire thing, divide by the x dot. So we do step by step. I don't want to do step 1, step 2 together in one expression because it looks very messy. So I will start with the green color step 1. Okay, so I have d dt, the dy dx, and you know that your dy dx is in the fraction form, so you have to use quotient rule. So d dt, then you have 2, and then bracket t minus s divided by 1 plus c. Okay, so you can start using quotient rule. Copy the bottom, which is 1 plus c. Differentiate the top. So when you differentiate the top, the 2 remains there. It's just a constant. So you have to differentiate t. You get 1. Differentiating negative s. Differentiating negative s would give you negative c, right? So you get a nice expression. 1 plus c, 1 minus c. Move on. Now you have to minus. Now you copy the top, which is 2 bracket t minus s. Then you differentiate the bottom. Now differentiating 1, you get 0. But differentiating c, you get negative s. You are supposed to get negative. But due to the negative in front here, so therefore this will give you positive s in this case. Now when I do, I try to reduce the number of negatives that I have. So I know this is going to give you positive, so I straight away put this as positive. So this whole thing is now divided by the bottom, which is 1 plus c in the bracket square. All right. So now we move on. Simplify. So when you simplify, you have 2 bracket 1 minus c squared followed by positive. Then you have 2 open the bracket. So you have ts minus s squared divided by 1 plus c in the bracket square. Okay. Now move on. So we have to, what is 1 minus c squared? Do you see there's this 1 minus c squared here? What is this 1 minus c squared?
S squared.
That will give you s squared, isn't it? So you can now change using the identity. So 2s squared. Wow, this is too thick. Okay, so you have 2s squared, then plus 2ts followed by minus 2s squared divided by 1 plus c squared. Now you see the 2s squared minus the 2s squared. So these two cancel out, left only 2ts. And that is the expression that you want, right? So you have 2ts, just keep it, divided by 1 plus c squared. You look at the result, the result is 1 plus c in the bracket cube. Now this is just the first step. Now I'm going to the second step. So to find d2y dx2, you need to use the expression that you have here, which is 2ts divided by 1 plus c in the bracket squared. This whole thing have to divide by 1 plus c one more time. Why is that so? Because the 1 plus c here is actually our x dot. This is actually our dt, dy, dx. So you have to remember to divide by the x dot. And therefore, that would give you the answer. Okay, so now you obtain the answer, which is 2ts divided by 1 plus c in the bracket cube. So now you have proven the result given. Okay, so far I think this one is okay. Now we move on to the last part. Now the last part is show that dy dx increases with x over the given interval of t. Now for this question, it's a bit actually it's quite easy, but a bit lengthy if you want to write down the solution, and you need to be very careful when you consider this one. All right. Now, when you read this question, show that dy dx increases with x over the given interval of t. And before that, before this question, they ask you to show that d2y dx2 is the given expression there. So there must be some connection between the d2y dx2 and also the next question. The next question asks you to show that dy dx increases with x over the given interval of t. So what is the connection between them? Can anyone tell me? Someone left. Who is that?
The ring is not here, so
Who?
Zheng.
Zheng not here.
Yeah, I don't know why. I call him, he didn't answer.
You called him and he didn't answer. Oh, okay. It's okay. So Zheng is absent, right? Can anyone tell me what is the relationship
If
between
d2y
the
dx2 if d2y dx2 is positive, then dy dx is increasing.
Yeah, actually, you have to go back to your P1, right? You have to go back to your P1. What did you learn in your P1? Now, P1 states that y is increasing function if and only if dy dx is more than 0, correct? And then the other way is, you say y is decreasing if and only if your dy dx is less than 0. Okay, so this is what you learn in P1. Right now, you want to show that dy dx is increasing. So you say that dy dx is increasing if and only if the differentiation of dy dx is positive. So therefore, d2y dx2 must be positive in this case. Okay, so now our objective is to show that the d2y dx2 that you found here is always positive. You need to show that this one is always positive. Always positive means more than 0 lah. So you need to show that this is always more than 0 for the given domain. So you must check. The domain given here is actually t in between negative pi and also pi. If you look at the function there, you have t, you have sine t, you have cos t. And for this region, t in between negative pi and pi, they have different signs, especially for the trigonometric term, right? You look at for cosine. So for cosine, the graph is something like that. So this one is negative pi. This one is pi. Highest value is 1. Lowest value is negative 1 for cos. This one is for cos. If you look at no, not this one. If you look at the, you have one more function is sine. All right, for sine, if you look at the sine, you have the graph something like this and this. Let's say this is y, this is x. So this one is pi, this one is negative pi. Highest value is 1, lowest value is negative 1. Right? You see, cos will be negative when cos is in between negative pi to, this is negative pi over 2. And then from pi over 2 to pi. So this part is negative. This part is negative. For sine, from negative pi to 0, the whole thing is negative. Right? So you have to be careful. When you want to argue for this question, right, you need to split the given interval t in between negative pi to pi into 2 parts. So how do you split it? You split this into when t is between negative pi to 0 and from 0 to pi. Okay, so you split into 2 parts. And now we can start arguing. For this cosine, we argue for cosine first. So since t is in between negative pi to pi, so for cosine, no issue. Why? Because from negative pi to pi, you know that your cos t is actually in between negative 1 and also 1. So now you add 1 to all 3 sides. So you get 0. Then this one is 1 plus cos t. Then this one is 2, right? And from this part, you already can see that your 1 plus cos t is greater than 0. So therefore, you can conclude 1 plus c in the bracket cube is definitely more than 0. This is what you want. Okay, this is what you want, yeah? Furthermore, you have t and also sine t. And now you have to consider t and also sine t, right? So for sine t, you have to consider from negative pi to pi. So I will split this into 2 cases. Or maybe I just do it like, okay, never mind. I do it into, I split this into 2 cases straight away. So you have to explain 2 times. So case 1, you explain saying that your t is in between negative pi to 0. So over here, you say that 1 plus cos t is always greater than 0. Cute. Or maybe because you want to show, so you just say 1 plus cos t is greater than 0. So this implies that 1 plus c cube is always greater than 0. So you have number 1. Okay. Then after that, you know that t is in between negative pi to 0. Yeah. What happened to your sine t? Your sine t is actually less than 0 as well. You look at the graph here, right? This part. From negative pi to 0, your sine t must be less than 0. Okay? And because your t is also, and because your t is also less than 0, so t also less than 0, these two combined, when they multiply, you have t sine t now becomes more than 0. Correct? So you have, therefore, 2 divided by 1 is always more than 0. So this implies that d2y dx2 is greater than 0. Now that is for case 1, yeah? Now we continue with case 2. Right, case 2 I use purple color. So consider case 2 now. So case 2 is when t is greater than or equal to 0, and then this is less than pi, right? So same thing, you have 1 plus c cube still greater than 0. This one is actually our 1, right? Then after that, you have t greater than or equal to 0. Sine t is also greater than or equal to 0. So these two multiply together, you have t sine t, and this is greater than or equal to 0. So this is number 2. So therefore, if you have, sorry, I call this number 3. 3. So therefore, if you have 3 divided by 1, that would tell you this is actually greater than 0. So that would tell you greater than or equal to 0. So you have d2y dx2 is greater than or equal to 0. So therefore, in conclusion, you can now write down. Therefore, for t in between negative pi to pi, right? Our d2y dx2 is always greater than 0. Greater than or equal, it doesn't matter. Okay. So you cannot stop here. You have to write down. What does it mean by greater than or equal to 0? So it follows that, or you can say by theorem, whatever lah. It follows that. Now you can say dy dx. What is the question again? It asks us to show that this is increases, right? So dy dx increases over, it increases with x over t. Increases with x over the interval t in between negative pi to pi. So that is the end of the solution. All right. And that's all my presentation today. All right. Thank you very much. And we will proceed with more examples tomorrow. So tomorrow, Thursday, I think I would meet you at 8:30 as usual. All right. Any question?